Welcome to our deep dive into object-oriented programming in C++. In this video, we'll explore the powerful concept of inheritance, which allows classes to derive properties and behaviors from other classes. This feature is fundamental to building reusable, maintainable, and scalable code. We'll start by understanding the basics of inheritance, move through its various types, and see practical examples that highlight its importance. Whether you're a beginner or looking to strengthen your C++ skills, this journey will clarify how inheritance shapes modern programming. Before diving into inheritance, let's briefly touch on the use of the const keyword with member functions. In C++, marking a member function as const ensures it cannot modify any member variables of the class. This is especially useful when you want to guarantee that certain functions like display or calculation methods do not alter the object's state. For example, a function that simply prints the sum of two numbers can be declared as const, providing both safety and clarity in your code. Let's look at a simple example. Imagine a class test with two integer variables, and b we have a set function to assign values and a disp function marked as const. The disp function outputs the sum of n b, ensuring that the function does not change any member variables. This approach is not only good practice but also helps prevent accidental changes to your data, making your code more robust and easier to maintain. Now let's shift our focus to inheritance. Inheritance is a cornerstone of object-oriented programming. It allows a class known as the derived or child class to inherit attributes and behaviors from another class called the base or parent class. This means you can reuse, extend, or modify existing code without rewriting it from scratch. Inheritance promotes code reusability and helps organize complex systems into manageable components. Why should we use inheritance? Imagine you're creating classes for different types of vehicles: bus, car, and truck. Each of these shares common features like fuel amount, capacity, and brake application. Without inheritance, you'd have to write the same code in each class, leading to redundancy and higher chances of errors. By using inheritance, you can define these common features in a base class and let the specific vehicle classes inherit them, reducing duplication and improving maintainability. C++, the class that provides its properties is called the base class, while the class that inherits from it is the derived class. The derived class can use all accessible members of the base class and can also add its own unique features. This relationship forms a hierarchy, where the base class represents a general concept and derived classes represent more specific implementation. Implement inheritance in C++, you use a simple syntax. The derived class is defined by specifying the base class after a colon along with an access specifier. For example, class derived public base. The access specifier determines how the base class members are inherited. This structure makes it easy to build complex hierarchies and extend functionality as needed. Access specifiers play a crucial role in inheritance. They determine how the members of the base class are accessed in the derived class. The three main access specifiers are public, protected, and private. Public inheritance is the most common, where public members of the base class remain public in the derived class. Protected inheritance makes public and protected members of the base class protected in the derived class, while private inheritance makes them private. Let's consider a practical example. Suppose we have a base class called shape which has width and height as protected members. The derived class rectangle inherits from shape and adds a method to calculate the area. By setting the width and height using the base class methods, the rectangle class can easily compute its area without redefining the properties. When you run the shape and rectangle example, you'll see that the area is calculated using the inherited width and height. This demonstrates how inheritance allows derived classes to utilize and extend the functionality of base classes, making your code more modular and easier to manage. E++ supports three modes of inheritance: public, protected, and private. The mode you choose affects how the base class members are accessed in the derived class. Public inheritance is most commonly used as it preserves the access levels of the base class members. Protected and private inheritance are less common but can be useful in certain scenarios where you want to restrict access. To summarize the access rules, in public inheritance, public members stay public and protected members stay protected. In protected inheritance, both public and protected members become protected. In private inheritance, both become private. Private members of the base class are never directly accessible from the derived class, regardless of the inheritance mode. There are several types of inheritance in C++: single, multiple, multi-level, hierarchical, and hybrid. Each type serves a different purpose and allows you to structure your code in various ways. Understanding these types helps you design flexible and efficient class hierarchies for your applications. Single inheritance is the simplest form, where a class inherits from only one base class. This is useful when you have a straightforward relationship, such as a car class inheriting from a vehicle class. The derived class gets all the accessible features of the base class and can add its own specialized behavior. Let's see a code example. We define a vehicle class with a constructor that prints a message. The car class inherits from vehicle. When we create a car object, the vehicle constructor is called automatically, demonstrating how the base class's features are inherited and initialized in the derived class. Here's another example using classes A and B. Class B inherits from A and adds its own methods. By calling setB, we can set values for both A and B and then calculate their product. This demonstrates how derived classes can build upon the functionality of their base classes, making code more modular and reusable. In this variation, setB takes parameters directly, allowing you to set values for both A and B in one call. The derived class B still uses the base class's methods and properties, showing the flexibility and power of inheritance in organizing your code and reducing redundancy. Multiple inheritance allows a class to inherit from more than one base class. This is useful when a derived class needs to combine features from several sources. For example, a car class might inherit from both vehicle and four-wheeler classes, gaining properties and behaviors from both. Let's look at a code example. The car class inherits from both vehicle and four-wheeler. When you create a car object, constructors from both base classes are called, showing how multiple inheritance brings together features from different sources. This approach is powerful but requires careful design to avoid ambiguity. Here's a more detailed example. The book class inherits from both author and publisher. Each base class has its own properties and methods. The book class adds its own features and can access all the inherited methods, demonstrating how multiple inheritance can be used to model complex relationships in real-world scenarios. Multi-level inheritance involves a chain of inheritance where a class is derived from another derived class. For example, a car class might inherit from four-wheeler, which in turn inherits from vehicle. This creates a hierarchy where each level adds more specific features building on the previous one. In the multi-level inheritance example, creating a car object triggers the constructors of vehicle and four-wheeler before the car constructor. This demonstrates how each class in the hierarchy contributes to the final object and how constructors are called in order from base to most derived. Let's see another example with classes A, B, and C. Class C inherits from B, which inherits from A by setting values in each class and calculating the product. You can see how data flows through the inheritance chain and how each class adds its own functionality to the final result. Hierarchical inheritance occurs when multiple classes inherit from a single base class. For instance, both car and bus can inherit from vehicle. This structure allows you to define common features in the base class and have multiple specialized classes that extend those features in different ways. In the hierarchical inheritance example, creating objects of car and bus both trigger the vehicle constructor. This shows how each derived class starts with the same base but can then add its own unique features and behaviors, making your code more organized and easier to extend. Hybrid inheritance combines more than one type of inheritance, such as hierarchical and multiple inheritance. This allows you to model complex relationships where a class might inherit from multiple sources and also serve as a base for other classes. Hybrid inheritance is powerful but can introduce complexity, so it's important to design your class hierarchies carefully. In the hybrid inheritance example, the bus class inherits from both vehicle and fare. When you create a bus object, constructors from both base classes are called, showing how hybrid inheritance brings together features from different sources. This approach is useful in scenarios where classes need to combine multiple aspects. Generalization is the process of extracting common characteristics from multiple classes and combining them into a generalized superclass. This helps reduce redundancy and makes your codebase more organized. For example, you might generalize properties like account number and balance into a bank account class, which can then be specialized into different account types. Specialization is the reverse of generalization. It involves creating new subclasses from an existing class by adding more specific features. For example, from a general bank account class, you can create specialized classes like savings account and current account, each with their own unique properties and behaviors. General classes define broad features while specific classes add detailed, specialized behavior. For example, money is a general class while dollar, euro, and rupees are specific classes. This hierarchy helps organize your code and makes it easier to manage and extend as your application grows. Generalization works in a bottom-up manner, combining multiple entities into a higher-level class. Specialization, on the other hand, is a top-down process, dividing a general class into more specific subclasses. Generalization reduces the overall size of your schema, while specialization increases it by adding more detailed classes. Polymorphism is another key concept in object-oriented programming. It means having many forms. In C++, polymorphism allows the same function or method to behave differently based on the context. For example, a person can be a father, husband, and employee at the same time, exhibiting different behaviors in different situations. Polymorphism in C++ is mainly divided into two types, compiletime and runtime. Compiletime polymorphism is achieved through function overloading and operator overloading, while runtime polymorphism is achieved through inheritance and virtual functions. Both types allow you to write flexible and extensible code. Compiletime polymorphism, also known as static polymorphism, is achieved using function overloading and operator overloading. This allows you to define multiple functions with the same name but different parameters, or to redefine how operators work for your classes. The correct function is chosen at compile time based on the arguments provided. Runtime polymorphism or dynamic polymorphism is achieved using inheritance and virtual functions. This allows you to call methods on objects without knowing their exact type at compile time. The correct method is chosen at runtime, enabling more flexible and extensible code structures. A real-life example of polymorphism is a person who plays different roles in different contexts. In programming, this means that the same function or method can behave differently depending on the object it is called on. This flexibility is essential for building scalable and maintainable applications. Inheritance brings several benefits to your code. It promotes code reusability, reduces duplication, and makes it easier to maintain and extend your applications. By organizing your code into hierarchies, you can model real-world relationships more naturally and efficiently. While inheritance is powerful, it's important to use it wisely. Overusing inheritance can lead to complex and hard-to-maintain code. Always prefer composition over inheritance when possible and keep your class hierarchies as simple and clear as possible. In large projects, inheritance helps manage complexity by breaking down systems into smaller, more manageable pieces. By defining clear base classes and extending them as needed, teams can work more efficiently and avoid duplicating code across different parts of the application. Inheritance works hand in hand with encapsulation. By keeping data members private or protected, you control how they are accessed and modified. Derived classes can use public and protected members but cannot directly access private members, ensuring data integrity and security. Abstraction is another key concept that works well with inheritance. By defining abstract base classes with pure virtual functions, you can create interfaces that must be implemented by derived classes. This approach enforces a contract and ensures consistency across different parts of your application. Many design patterns in software engineering rely on inheritance. Patterns like factory, observer, and decorator use inheritance to provide flexible and reusable solutions to common problems. Understanding inheritance is essential for mastering these patterns and building robust applications. Recap: inheritance is a fundamental concept in C++ that allows you to build complex, reusable, and maintainable code. By understanding the different types of inheritance, access specifiers, and related concepts like generalization, specialization, and polymorphism, you can design better software and tackle more challenging projects with confidence. In working with inheritance, always plan your class hierarchies carefully. Use inheritance to model real-world relationships, avoid unnecessary complexity, and leverage polymorphism to write flexible code. Remember to use access specifiers appropriately to protect your data and maintain encapsulation. Thank you for joining us on this journey through inheritance and related concepts in C++. With a solid understanding of these principles, you're well equipped to write efficient, maintainable, and scalable code. Keep practicing, explore more examples, and continue building your expertise in object-oriented programming.